So if we want to do the critical value rejection region approach to the z-test, we have a very similar set of steps, just with different pieces moved around in different places to correspond to the change. For this, first, what we're going to do is verify the conditions that we need. Again, it's basically a free step. Then we state our hypotheses and identify the claim, and specify the level of significance. So, first three steps, exactly the same. From there, things get a little bit different, though, as we want to find the critical value instead of going on to the test statistic. But once we have the critical value, then we need our rejection region. So it's kind of like that p-value idea, except we're looking at it in a slightly different way. And from there, we get the test statistic, make our decision, and interpret our result, where our interpretation and our result depend on whether or not the test statistic falls into there. We'll see what that looks like with the following example. So, here we have that a researcher claims that the mean annual cost of raising a child under 2 by a married couple family in the United States is $14,050. In a random sample of such families in the US, the mean cost of raising such a child is $13,795. With that sample consisting of 500 children. Assume the population standard deviation there is $2,875 for alpha equals 10%. Do we have enough evidence to reject the claim? Okay, so starting from the same place as before, if we want to check these conditions, again, we have 500 kids in this sample, and we have the necessary parameters, so we're all good on that first step. For the second step, we want to talk about our hypotheses and claim. In this case, it's a little bit subtle, but look for that word claim. We have that the researcher is claiming something about the mean. This is not research that they're presenting in some way. This is research that they are anticipating. They are anticipating a mean of 14,050, and don't ask me why I bothered to write the units for this one. Who knows? Just fall into that pattern, I guess. But that is our claim. The opposite of that claim is that it's, well, anything else. So don't get thrown off by that sample mean there. It doesn't actually factor in directly to how we write these hypotheses. The hypotheses are always in terms of what we think should happen to mu, where equality is the null, non-equality is the alternative, and this is one of those oddball cases where the null hypothesis happens to be our claim. It does happen, but it's generally less common. Once we have our hypotheses, we move on to the level of significance. In this case, level of significance, alpha, is that given value of 10%. So they're willing to take a bit of a chance here with their research. They want the result a tiny bit more, maybe. But anyway, here we have alpha as 10%, and the test in this case will be two-tailed because the alternative hypothesis is the general inequality. Whichever we have as our claim doesn't actually affect whether the result is one or two-tailed. That is always determined by the alternative hypothesis. Here, it's two-tailed. Then from this, well, we need to get on to our pieces involving things like the critical values and the rejection region. So for our critical values, since this is two-tailed, what we're going to have to do first is split up that alpha into the two tails, where we're going to get one from each tail. And to get those values, we're going to do something with a thing like the inverse normal function, where we want to find the amount with 5% on each side, making a distribution picture something like this as what's popping up. And don't worry, it's a spoiler in there, just don't pay too close of attention. But we're going to split that up, and we're going to get our critical values here, which usually get denoted with something like z-naughts. Here they're going to be from the inverse normal, so I'll say plus or minus inverse normal, where we want something that we're coming out with here having a 5% from there, or if you want to do 95%, you get to the same place. Point is, you get that these happen at about plus or minus 1.645 as on the picture. So our rejection regions are going to be values above 1.645 and below negative 1.645. So it's kind of hard to picture these, like I said when we were talking about this back in the last section, because the determination of the rejection region depends entirely on what happens with the tails that we're working from. Spaced out for a second there. But whether we're looking for things above and below, above or below, it depends entirely on what kind of test we're running, and then the location also varies a little bit based on circumstances. But these are our critical values and rejection regions. From there, we want to get the thing that we're going to actually compare it to, the z-score, the test statistic, but it's still the same test statistic, x bar minus mu over the standard error term, sigma over root n, which in this case has the flavor 13,795 minus 14,050 divided by 2,875 over the square root of 500. It's a very, very nasty number that we're not going to worry about. The calculator is going to do this for us and give us a value that will be approximately negative 1.98. So if we wanted to do this with the p-value, what we would do is we'd take that, we'd flip it back over to the other side, and we'd use some sort of computation to find those p-values on either side, where we get some p-value on top of that I'm not going to write in here because that's not what we're looking for. But in this case, we see this value, negative 1.98, is below negative 1.645. This is less than one of our critical values. It's less than the smaller critical value. Importantly, it's technically less than both, but it's not so useful to be less than that one. Anyway, it's less than that. As a result, when we are making our decision, we will reject the null hypothesis. So this researcher's desire for a result may have backfired on him because as a result of this decision, our interpretation is something to the effect of there is enough evidence to reject the claim that the mean annual cost of raising a child aged 2 and under by married couple families is $14,050. Where if we want to do this, we could work with it in a similar way using the z-test function, using the z-test functionality in the calculator, where a couple things to notice are that one, that functionality does not by default give anything in terms of the critical values. It doesn't actually have any input at all for that. And two, it doesn't actually give you the final interpretation. It only gives you the p-value. So that's really the big danger of working with the calculator for these types of problems, is that all you get is a bunch of numbers. And it's on you to be able to read those numbers and know what they do. Statistics is an interpretive science. So these are interpretive problems. But you gotta be careful. Whether you want to use critical values, p-values, either will get you to the same place. In this case, a rejection of the null hypothesis, and as we'll see later, maybe something else. But that's all we're going to see for 7.2. That's all we're going to see for dealing with the z-test case. So in 7.3, we're going to move on to a perhaps more reasonable setup, a perhaps more reasonable conceptualization, where instead we don't assume knowledge about sigma, we assume sigma is unknown, and we work using the t-test instead, using t-scores. But we'll save that for 7.3, which we're going on to right now.